My talk today is about APIs of the future. And the question is, are you ready? This is really our chance to think about what kind of things we can expect to see. We've made so much progress in the last 10 years on APIs, and it turns out we're standing on the shoulders of giants. I'm going to talk about the past of APIs almost just as much as the future. And that to me is very exciting as well. But I think we've got an amazing future ahead of us. I think we're actually on the cusp of a new set of paradigms in the way we use API and modular programming, modular thinking, the very same thing that Saul was talking about before. Before we start, I just want to say this is me. This is how you find me on LinkedIn and YouTube and GitHub and Twitter, and I would love to connect with you. This is the way I get to travel. I used to travel around the world about 40 weeks a year. Now I've traveled down the steps into my basement here to the studio space and get a chance to visit with all of you today. So please connect. Tell me what's interesting. Tell me what's challenging. Tell me what you think the future of APIs will be, and I would love to be able to share that with others. So these are two projects that I've worked on recently. The design and build of great web APIs with Pragmatic Publishing came out just a little over a year ago. And we're just about to release a new edition of Continuous API Management. I'm co-authoring with Mehdi Majoui and Eric Vilda and Ronnie Mitra. We're very excited to bring that work to you as well. But what I want to talk to you is this notion of APIs of the future. And I want to do it in my typical way of kind of looking back as much as looking forward. So I want to talk about what I call that first age of computing, where we were, where we're coming from. I think we're in what I would call the second age of computing. We're making lots and lots of progress, taking advantages of many things, but I think we're kind of closing out that second age, and we're getting close to that third age of computing, where I think things will be vastly different, just as exciting and just as powerful, but will be done in a very different kind of way. So I want to start out with where we were. I want to talk about the history of computing, and I want to take us back to 1850. A lot of people don't really think about the history of computing as starting in the mid-19th century, but that's where I think it really begins. And I think we can learn a lot of lessons from the very first programmer that we know of, that we credit with computing. Now, this is what computers looked like in the 19th century. This is basically a difference engine or analytical engine. This one is built by Charles Babbage, and it was a series of pins and gears and levers, and you would actually wind up these levers, set the pins in a certain way, wind forward, and that would give you the answer to a problem. This is actually one of the first known programs, first known computer programs. It computes a series of numbers called the Bernoulli number series. And as you can see, it's written all in these, it's kind of hard to see on the screen here, but it's all these setups of these various gears and levers and knobs in order to make sure that they're all set correctly. And then a single turn of the crank would give the next set of pins that you would then decode to read what the next number in the Bernoulli series would be. But this is the first known working program. This is the first known working programmer, Ada King, Countess of Lovelace. She was a mathematician, and she was one of the first people to figure out how we could use these analytical engines to solve mathematical problems. In fact, Babbage, the person who created the machine, mused in letters to many people and backers. He wasn't quite sure what the difference engine could be used for. Ada King knew right away. Countess Lovelace knew right away. And what I find really fascinating is this quote from King, that the analytical engine weaves algebraic patterns the way a jacquard loom weaves flowers and leaves. A jacquard loom was a loom for creating blankets and tapestries and things like that. And the analogy is really, really quite striking. This is what a jacquard loom looks like. This is a recreation of one. And you would actually use the same kinds of ideas, set pins and knobs and gears in order to create patterns in clothing. This is also one of my favorite quotes from Ada King's work. Debugging is damnably troublesome work and it plagues me. So here we are, the very first programmer, the very first program, and we're already problem with, she didn't say debugging, but she was talking about solving problems. And I would point out, by the way, that Ada King was a remote worker. Ada King was not working in the same room where the difference engine was. She would write out the programs, mail them to Babbage. Babbage and others would program them and then tell her the results and tell her whether or not the results matched up. This is a really tedious work. We think remote work is troublesome today. Try doing it through the post. Try doing it through the mail service. Now, later into the 19th century is a person by the name of Ottley. And he has this notion of starting to get computers now towards the turn of the century. We're getting electricity, we're getting radio, we have the notions of moving pictures, and he has this notion that computers should be connected together to create a network so that we could see any bit of information from any location. This was right at the turn of the century. This is a picture of what Ottley thought the network would look like, what he called the mundanium, like all the details of the world. And it connects video and audio. You could zoom in on an opera performance, on a concert performance, read a book at a distance. And this is what he thought a workstation would look like. This is a rebuilt model of the workstation that Ottley thought we would all be using in the future. And it has radio, recording, microfiche, pictures, photos, cards, all the material that we would want that we could call up in order to find information. This is what he called the worldwide network at the turn of the century. Now we get close into the 40s, in the 1940s. This is what computing looked like in the 1940s. This is a giant room. This is one computer dedicated only to computing the mathematical challenges of trajectory of missiles. And you can see someone in the front mugging for the camera with a few knobs. In the back, I believe that's Kay McNulty in the far back and Gene Snyder in the front. These are the people who actually programmed the computer. These are the ones who understood exactly how you had to set this up. And these are the programs that they wrote. Notice that this has some familiarity with the charts from King, but now what we're seeing are wiring diagrams. These actually indicate the exact wires that you plug in from step 1 to step 2 in order to set up the computer to make one computation. So rather than setting gears and pins, we're now setting wires. This is the group of programmers that actually made the ENIAC, the very first electrical computer work in the 1960s. Snyder and Jettings and McNulty and Meskoff and Lichterman and Billis. These are the people that actually programmed that very first computer. This is what it took. This is what it was like. We're going to need to plug this in here and this in there. We didn't have any programming. We didn't have programming tapes or anything. What we had was just simply wiring diagrams. And every time we wanted to change the computation, we had to rewire it and retest every step of the way. We get an advancement to wiring diagrams with this. We get the punch card. The punch card comes to us right around the 30s and 40s, before the computing happens, but we get to apply them to computers around the 1950s. This is the first IBM computer that starts using punch cards. The person in the front of the picture is Lois Haight. Lois was one of the creators of the Fortran language. She was on the team that created the Fortran language. And this was an IBM computer at the time. I think this is the 70 series, which later becomes the 700 series. The 700 series is used to monitor and manage the US space program through the 50s and 60s. And the person who ran the space program, who actually used the Fortran to compute trajectories of missiles, was one of the people was Dorothy Vaughan. She really ran most of the activity for NASA for computing. So now we have punch cards and computers, and we're getting more advanced computers by the time we get to the 1950s. And that is sort of the pinnacle of what I call the first age of computing. We went all the way from the difference engine, the analytical engine, to this card sorting machine that could launch vehicles into space. That's an incredible distance to travel in just 100 years. By the way, this is the back of the Jacquard loom that I showed you earlier. And you can, if you zoom in, you can actually see why Ada King, Countess Lovelace, said that programming was very much like the Jacquard loom. And this looks very much like punch cards. So even though she had never seen the idea of punch cards, she understood even then what computing would be like in that first 100 years. I find that just fascinating. So we're in the second age of computing, one that starts around 1950. We have mainframes. We start with this notion that we can actually have lots and lots of computing power. I want to jump ahead. There are lots of things we could talk about in the 50s and 60s, but I want to jump ahead to 1968 and this man, Engelbart, who gave a demo in 1968 about what he thought the future of computing would be. And this demo was an incredible event. Remember, this is at a time when basically we have punch cards that we feed in and we get paper printouts. What Engelbart starts talking about is this notion that in 20 to 30 years, that would be, say, like the end of the century, the 1990s or the year 2000, we'd be able to hold in our hands as much computing as exists in the entire world. And boy, was he right. He gave this presentation in 1968. It was like 90 minutes long, just him on the stage with a big screen. And he showed things that we take for granted today that seemed magical at the time. The idea of picture-in-picture, the idea of actually editing lists on screen. So we have interactive computing. He actually even created his own computing keyboard. He invented the mouse. He's credited with creating the mouse just so that he could do his demo. Notice the paddles he has in his left hand. He hardly ever used the actual keys. He mostly used the paddles and the 3-button mouse. He introduced in this one event real-time in-place editing, point-and-click, hyperlinking, intelligent outlining, text messaging, live video and text at the same time, revision control, all these things that he said in 1968 were possible. No one believed him. They thought he was just a nutty person. But of course, we get all of those things. He even invented his own chair. This is a specially built chair from Ames Corporation, just for this purpose. Now, one of the key elements of Engelbart's work was this reliance on links, hypermedia, hyperlinks, which were created by Ted Nelson. Ted talked about these in the 1970s. We couldn't have the APIs we have today if it wasn't for links. Ted's vision of what the internet would look like would be all of these documents connected together, not machines and performance, but actual documents that were connected together. We would be reading one scroll, which was actually the source of lots and lots of material. This is what he called the docuverse, the Xanadu docuverse. He wrote a very interesting pair of books, which is called Computer Lib and Machine Dreams. There are actually 2 books that were back to back to each other, large size like books. We would say in American measurements, 11 by 17, 11 inches by 17 inches. I'm not sure which A that is. Somebody else can translate that for me. An incredible series of books where he talked about how computers would unlock information and allow you to mix and match them. The first person to actually build a system that was widely used based on Ted's ideas and Engelbart's ideas was Wendy Hall, now known as Dame Wendy Hall. She was a mathematician. She was asked to collect all of the archives of Lord Mountbatten in England. And she decided the way to do this would be to do it electronically. And she and her colleagues invented a system called microcosm. It was the first hyperlinked system of video, audio, and text all together. And that she built this system called microcosm, and it was running in like 1986, 87, and 88. So it was up and running before Tim Berners-Lee actually had his very first web server running. She had an entire system working using IBM tools at the time. Now, along with the work that Hall had been doing in collecting information, Goldberg and Kay were working at the Xerox PARC location where Engelbart had also worked. They were developing things like the Smalltalk language and object-oriented programming, and another key element in the story, the dynabook, the idea that we could actually take a mainframe or take that desktop machine that was sitting on Hall's desk and turn it into something that was originally called a luggable, a carryable, you can see at the bottom of the screen here. But it goes even further. Eventually, Kay and Goldberg said we would all have something that would sit on our laps. It would be like a book, but only better. Now, what they started with was the computer system on the right, the Altair system on the right. What they wanted to get to was a computer that sat on our laps on the left. And of course, by the time we get to the end of the century, we have just that, which is really, really quite amazing. By the way, now we're not programming with pins, we're not programming with wires, we're not programming with punch cards, we're actually programming in text. This text is the same program of Ada King's, Countess Lovelace Bernoulli number series, but notice it's written in a language that's named after Ada. It's called Ada. It's a language of Ada named after the very first programmer, which I find just really fascinating. So now, because of the work of all these individuals in this second age of computing, we get things like the Wikipedia, where people can contribute from all over the world, the way Engelbart talked about. We can have all the information at the palm of our hand. We can have it in a simple laptop that lets us go all around the world and actually lets me talk to you today. And I think that's really quite amazing. So where are we going? What will APIs be like in the future? What role will APIs play in all the things that we're doing? So think about it. We've gone from Lovelace with the tables and mechanical computers and Babbage, from McNulty, electrical relay computers like ENIAC, and Vaughan's Fortran for IBM, and Engelbart's text screen for computers like Wendy Hall built. What's next? Well, here are the things that I think we need to pay attention. We need to look out for in the coming days. We are going to be connecting services the way we currently connect servers. Remember Nelson's docuverse, the idea that we could scroll through something and actually be reading parts of different documents at the same time. That's what our APIs will be like as well. We'll be stitching things together just seamlessly into pieces. We'll be programming the network instead of programming machines. Too much of what we do today is programming a machine and placing the machine out to have that machine interact. We'll actually start programming the interactions directly. Lambda services and cloud services are our first bridgehead into doing that as a normal course of business. It will no longer be where we place computers or where we place our programs. It will be the program itself. We'll focus on describing problem spaces, not describing solutions. We'll actually program computers to actually understand what's going on in the problem space. And we'll describe that problem, and then other people can write solutions, or maybe even computers can write the solutions themselves. Machines, endpoints, protocols, formats, all that stuff will disappear. Instead, we'll be talking about a whole series that's kind of the seamless universe. So connected services, what we think today looks like big balls of mud, that's how reality works. That's how the internet works. That's how nature works. That's how biology works. And that's how our computers will work as well. We're going to be programming software-defined networks today. We're going to be doing all our kind of programming in the network in the future. The network itself will be the material that we use to program with. We'll be describing those problem spaces using languages and diagrams, and those diagrams and those languages will be understood by computers themselves. They will understand how to come up and solve a problem. We'll be much more declarative than we are imperative today. And all those details of endpoints will go away. Here's a sort of an experimental language, a kind of a network language, where we're basically connecting to various services. There are multiple service connections, and then we're going to do some shopping, we're going to check out, and we're going to pay. There are no addresses here, there are no URLs here. This is simply a language dedicated to solving a particular set of network challenges and network problems. And that's what we'll be doing more and more of. So just as we change the focus from memory to text to the cloud, we're going to actually change our focus to actually solving problems with multiple machines. So how do we get ready for this? What do we need to do? So what we can do right now are a handful of things. First of all, low code and automation are all heading us towards that same place of coding the network and describing problems. So be prepared, pay attention to low-code systems. Whether you like them or not right now, they represent another way of thinking about computing. And that way of thinking about computing is a much higher level. And we're all going to be doing that in some form or another. Start taking a look at decentralized orchestration. We have IFT and Zapier and lots of other systems like that, Microsoft Flow. That's just the tip of the iceberg. We're going to be connecting computers in lots and lots of different ways. Think of the way Lambda works today, but with almost zero cost and zero barrier of entry. That's what we're going to be building. So how do we start orchestrating various pieces of software living in various places safely, easily, and quickly? And then the other thing that I think we need to pay attention to is the return of domain-specific languages. So Parsons and Fowler wrote a great book several years ago on domain-specific languages. I would dust that off, take a look at that, start reading that again, because I think we've already seen DevOps create new domain-specific languages. RPA and low code is going to do the same thing. Think ahead. Think about a GDPR language or a HIPAA language or a BIAN banking language or a FHIR health language or an Accord insurance language. We'll be programming in languages. COBOL was originally a dedicated language. Fortran was a dedicated translator for math language. We're going to be having lots and lots of those languages in the future. Now, at the same time, I would say you're going to want to watch out for chatbots. Be very wary. Chatbots right now are a dangerous place to be. There's a lot of romance around them, but right now they can be very, very troublesome. And they don't really offer the chance for advancement that we really need. In fact, I think what you need to focus on instead are something that I talked about here at API Days several years ago: task-focused microworlds, domain-specific languages, domain-specific intelligence, domain-specific chatbots. Think about donotpay.com that helps you resolve parking tickets. Lots of health experts actually analyze documents and help diagnose in ways that humans can't. Copilot at GitHub is trying to do this. I'm not sure that it's the right direction, but we're going to see more and more of these kinds of things in the future. If you want to stay informed on AI and machine learning, here's two people I strongly recommend you pay attention to. Melanie Mitchell has written some fantastic books about what artificial intelligence really is. Her primary work is whether or not a computer can recognize or tell a joke, understand irony. These are fantastic topics. Now, Joy Bolamwini has written a fantastic book on code bias, and that's going to be turned into a movie sometimes really soon. She really has a handle on the troubles that we run into when we work with machine data, machine algorithms. These are two people that I would pay close attention to. They'll lead us towards the direction where AI and machine language can be equitable, safe, and powerful. I've actually started a project on DSL languages, so you can actually look up HyperCLI or HyperLang if you want to learn more about this project. These are examples of actual programs that work. I'm not going to spend too much time on that. I'll let you take a look at that as well. But all of these lead to the same notion: programming services with a network using specific languages to enable task-focused bots operating in well-described problem spaces. That's our future. We can start working on that today and make that a reality. And I just want to leave you with one more thing. We have to learn from the future. I love this quote from Joseph Miller: "Those who ignore the mistakes of the future are bound to make them." Think about that. We know what's possible. We know what could go wrong. We can prevent bad things from happening today. We can pay attention to what is important, what makes sense, what's fair, what guides us, what's safe, what protects our privacy. Let's do those things today and not make the mistakes of the future. Let's not ignore those mistakes. Now, if you like some of these ideas, I'm working on a book for 2022 called RESTful Web Microservices Cookbook. It's going to cover a lot of these ideas, a lot of these DSL type ideas, a lot of service-to-service communication, and how we can actually start defining problem spaces in order to create solutions. So if you like that, there's more on the way. So I just want to say thank you very much. I'm very excited about APIs of the future. I'm doing everything I can to be ready, and I hope you will too. Thank you very much.